So, welcome back to this class once again, where we are talking about the production of fluorine gas, and our byproduct was hydrogen gas also. So, we have to use the electrolysis cell, and the corresponding structure of that particular electrolysis cell we have already discussed. So, now we see the diagram, the flow diagram for it. So, if you have a simple, basically these are all big chambers, you have the monel or the steel made container, and you have the corresponding cathode material of it. And as I told you that these spaces are basically separated. So, you have multiple numbers of cathodes and anodes over there. So, if the corresponding whole material of this particular cell is one type, then you can have the corresponding anodes over there. So, is basically a flow diagram for your industrial fluorine cell, where we can utilize the corresponding electrolysis of your HF present in a melt. So, one basically the number wise is you have the cooling jacket, because you have to cool it, because sometimes during the production your temperature may go rise. Then you have number 2 is your hydrogen outlet. So, hydrogen outlet from these electrodes, which are very close to your steel skirts number 4. So, you have only 2 outlets, one outlet is for fluorine and another outlet is for hydrogen. So, you are happy that you can take out these 2 quantities what we are producing through electrolysis, from one is from the anode and another is from the cathode. Then number 3 is fluorine outlet, number 4 is the steel skirts, these lines, number 4 lines, all these lines are steel skirts for separating the gas above the melt, because you have thing. So, the 2 bubbles basically the hollow and the solid bubbles, one is for the cathode and another is for anode. So, from the bottom, these are the bottom of the melt, and through the side of these electrodes. So, these are basically is connected to the body of this electrolysis cell is one type. So, this is one type, and this is the body and this is the body. So, you have the 3 black one and 2 lighter one, the anodes. So, these bubbles are coming out, and when they are accumulating, basically these bubbles or the gases have to leave the melt. So, when it is going up, basically these steel skirts are hanging from the top when it is the vacant space where the gases are being stored. So, they are not getting contaminated if they are separated nicely. So, this separation basically giving you this one. So, this particular chamber giving all these gases, and you have only one outlet. Similarly, for this one also you have all these gases around this electrode, but you have one outlet. Similarly, from the side of the electrolysis cell, this side and this side, you have this, and only you have the electrode outlet, that is your hydrogen. So, hydrogen from the cathode and fluorine from the anode will be produced, and this particular one originally developed by US Atomic Energy Commission, because in our country as well as everywhere there will be constant demand of your fluorine supply. That we will also see for the uranium enrichment. Uranium hexafluoride is also one of the good species. So, like our BRC in our country, so United States Atomic Energy Commission has also developed this particular cell, because most of these material are sometimes is patented. So, is the US patent you can have all the time. So, this thing, the idea is that very simple, that how you get this, and when you get this particular one. So, we get fluorine, and fluorine is obtained is directly processed further. So, once you get from the electrolysis cell the fluorine, so you can utilize that particular fluorine for making uranium hexafluoride. Just now I told you that you can make it UF6, or sulfur hexafluoride SF6, tetrafluoromethane, where all the hydrogen atoms of the methane can be substituted by fluorine, or fluorographite. So, one good material, that means the modification of the graphite material you can have, because the graphite is only that carbon containing material, but if you can have some amount of fluorine in it, so it can have the fluorographite type of thing. So, this particular one, so the carbon of that particular graphite that means you have the corresponding that graphite sheet, we know that the corresponding benzene rings are there, that means hydrogens are there. So, those hydrogens will be substituted by fluorine, will giving you the fluorographite, will have a high conductivity. And another one is a very useful material nowadays during the last 10-15 years through the work on the graphene material, the production of the graphene, how you get good amount of graphene from the graphite sheets. So, these graphenes are mostly useful. So, fluorographene we use for making the battery, the lithium ion battery, the sodium ion batteries and all these things. So, this fluorographene, making this fluorographene is also a very useful or a challenging task, or sometimes you can liquefy it with a boiling point of minus 188 degrees centigrade. So, the liquid fluorine gas, so liquefied fluorine gas, to transport from one particular place, that means the site of production to the site of consumption. So, is filled into pressurized cylinder, the way we pressurize the different gases like our CNG or LPG gases for our cooking. Similarly, this fluorine gas can also be filled in all those pressurized cylinders. Then we can have this fluorographite or graphite fluoride, what we call. How we make it? It's very easy to have your graphite material in your hand from any good carbon source. So, it's basically the fluorination of the graphite material. The fluorination of your graphite material at high temperature reaction, that means is a gas phase reaction, is not a thing that what we consider, because we'll little bit if we are able to consider that, considering the fluorine, because fluorine is a very useful atomic center for making the drug molecules, the pharmaceutical molecules also, because the activity drastically changes. If you have a drug molecule or the medicine having a CH bond, and if you move from a CH bond to a CF bond, the reactivity pattern and all these things are drastically getting changed. So, large number of these all medicinal molecules are available where you have carbon fluorine bonds. So, fluorination of those organic molecules will also be interesting. But here if we just try to have a material which is a graphite material and we only just go for the fluorination. So, you use the fluorine gas either from the cylinder or in situ production, that means immediate production, that means you must have the corresponding electrochemical cell and you directly produce fluorine gas and pass over there. So, with graphite charcoal, so basically is a very raw material, that means graphite thing you can have purified form or simply the charcoal. Charcoal is your good carbon source, or pyrolytic carbon powder. We all know that the carbon in our country also large number of companies are making carbon powders, carbon black and all these things. Is a very cheap quantity thing what we put in our cycle tires, our car tires and all these things for increasing the thermal conductivity. So, those material can also be utilized for the fluorination. So, you get the corresponding graphite fluoride or the fluorographite. So, is the precursor also for the preparation of graphene fluoride by a liquid phase exfoliation. So, the technique which is applied, that means layer by layer removal from your graphite block or graphite sheet or whatever it is. So, the layer wise, if you are able to remove one of the layer from that graphite surface, it is your graphene. Graphene is nothing but a sheet. So, the liquid phase exfoliation, the technique is known as exfoliation, that means the layer wise removal of that graphene sheet from the graphite material. So, you make the graphite or the fluorographite or the graphite fluoride and then you try to get the graphene fluoride, because the fluorographene are also very important material for industrial application. Where we use this fluorographene? Fluorographene is the material first described not very long ago, it is only in 2010 by Robinson et al. The person who was doing is Robinson, using graphene grown on copper foil. How it was discovered for the first time? Because you make a material, you produce a material, you never know that the material will be highly useful afterwards. But as an academic interest, we do basically in the laboratory, sometimes we have that excitation that why don't you make some new molecule or new material out of this. So, he thought that it can be used from that particular one when that graphene basically is utilized for the fluorination on a copper foil, because if you have the graphene on copper foil, it can be deposited on the copper foil and is simply exposed to not your direct fluorine gas from the cylinder, but another molecular compound which is xenon difluoride XCF2 at only room temperature, higher than room temperature. In our country, we most of the time we have this is our room temperature 25 to 30 degrees centigrade. So, if it is exposed to xenon difluoride, you get the corresponding fluorographene. So, this is the most useful technique, not the other fluoride compounds of xenon, that means xenon tetrafluoride or xenon hexafluoride. It is only the difluoride. Difluoride would be useful to give you the fluorographene compound. So, next we will just go for the preparation of hydrogen fluoride. So, fluorine gas is gone. Now, we go for the hydrogen fluoride gas, which is also like that of your hydrochloric acid gas or hydrogen chloride gas, is hydrogen fluoride gas HF, which will also be very much useful material in different industries. So, again we will take the help of fluorspar. The fluorspar will be your raw material, but now it is the acid grade fluorspar. Treat it with sulfuric acid. Earlier we were treating in presence of bauxite. Now, in absence of bauxite, we treat it with sulfuric acid and heat it in a rotary tube furnaces. So, you take a different type of furnace now, definitely since these are all industrial production, we have to use some reactor or some furnace. So, now you have, instead of calcium fluoride sulfuric acid, alumina last time, the same reaction without alumina, only Al2O3. So, you stop it, you get 2HF plus calcium sulfate, because we are not interested to have the corresponding aluminum fluoride. So, this when then is treated with silica, that we have seen that you can have the hexafluorosilicic acid or silicon tetrafluoride. So, when the produced HF you utilize to treat the quartz or any other bad quality of silica also, quartz is the good quality of silica. So, you have this silicon dioxide, that means silica, which is treated with HF. So, is giving you silicon tetrafluoride. So, that is the basic or the underlying principle we all know, that the glass surface, etching of the glass surface, if we go for the etching of these glass surfaces, we use HF because the silica present in it on the glass will be destroyed through the formation of silicon tetrafluoride, and that as a gas material will be escaped away from there. So, how you go for this reaction? The reaction is carried out in an indirectly heated rotary tube furnace. So, as I told you, this is a rotary, not only rotary furnace, is a special type of furnace, but is a tube furnace where the length is 30 meters and diameter is up to 3 meters. So, it is a huge one. So, 30 meter in length and diameter of 3 meter, but is a tube shape and a high temperature withstand of 200 degrees centigrade. So, it is a very high temperature reaction to treat your fluorospar by sulfuric acid. So, in an indirectly heated rotary tube furnace where we can use of the same dimension, that means 30 meter of length and 3 meter of diameter at high temperature, temperature is basically a 200 degree centigrade. So, this heating procedure is basically giving us the corresponding production of your hydrofluoric acid, and the byproduct in this production of hydrofluoric acid is that if you have, as I told you, that you use silica or quartz for taking up your HF production for its conversion to silicon tetrafluoride or H2SiF6. But sometime your silica SiO2 is already present in your fluorospar. Your quality of fluorospar is not so good that it has already silicon dioxide or the silica material in it. So, whatever HF you produce there, so in situ the produced HF will attack your silicon dioxide, and that silicon dioxide will produce SiF4, and ultimately in presence of excess HF it will be producing H2SiF6 or hexafluorosilicic acid. So, this is the reaction what you get over there, that means whatever formed as silicon tetrafluoride, which will be your gas, the same basic reaction for etching of the glass surface will trap. So, during its the escape passage of your silicon tetrafluoride, which is also a gas material, will take up the HF, because you have the HF in the liquid phase, aqueous HF. So, it will take and will remain there in the aqueous medium as H2SiF6 instead of HF. So, you have large amount of H2SiF6 along with your HF. So, you have to separate these, that means H2SiF6 has to be separated to increase the concentration of HF or to increase the purification process or to improve the purification process of your HF, such that a good quality of HF you can have. Because most of the time for our laboratory use also, HF what we are getting, some aqueous solution only, say 40% of HF we get for the day to day laboratory use. Sometimes it can have the corresponding 60% or 70% HF in the aqueous medium. So, most of the time you take that particular material, that means the raw HF which is available in the aqueous medium as the corresponding one. Only thing that you have to level it, you should know the corresponding concentration, whether it is a 40% HF bearing aqueous HF or a 50% HF bearing aqueous HF. Then we can utilize for the different applications. One such application for making is the direct inorganic fluoride making. As we have seen earlier, that directly using fluorspar and sulfuric acid we can make aluminum trifluoride or aluminum hexafluoride. Then we now use that particular one in a large scale for the manufacture of one such useful inorganic fluoride is the aluminum fluoride, because for getting aluminum out of that as your cryolite, because the cryolite is a naturally occurring material. Similarly, laboratory prepared or the industry prepared aluminum fluoride as cryolite Na3AlF6 can also be utilized for aluminum production. Then uranium tetrafluoride UF4, sodium fluoride, one very useful molecule which used in all the laboratories, all the research laboratories, in all organic chemistry laboratories is the boron trifluoride BF3. Then ammonium hydrogen fluoride, ammonium bifluoride, what we use in typical analytical chemistry laboratory classes also is a typical masking agent, because it reacts very quickly with the iron present in it. So, if we try to remove iron from any medium, that means the color from that medium also, that iron always we know in the ferric state it is basically light yellow to orange. So, to remove that particular one, we add excess fluoride as ammonium hydrogen fluoride and ammonium bifluoride, ammonium HF, ammonium bifluoride. So, the entire iron can be taken away as FeF6 minus. So, it is also decolorized and you can take out that particular one. Even for the titrometric procedure for analytical chemistry, you add this and you can avoid the iron estimation, because this iron will not interfere during that estimation. Suppose we are analyzing iron and copper together. Then it is utilized for the manufacture of different organofluorine compounds, particularly fluorohydrocarbons or corresponding fluoro derivative of the ethylene, as I told you earlier, that you can make it tetrafluoroethylene for the preparation of Teflon. So, the tetrafluoroethylene preparation is also a preparation of your fluorohydrocarbon type of material, and sometimes a very good quality, that means your material is highly pure and a small amount can be utilized as a good catalyst. So, it is a useful catalyst for alkylation reactions. If we want to put more number of alkyl functions on a particular type of carbon center, we say that we are going for alkylation reaction, such that you have a methyl function which is CH3. You can go for is a tertiary butyl function by replacing all the 3 hydrogen centers or the hydrogen atoms by 3 methyl groups. So, is basically a methylating process or methylation process, because it is a very useful reaction. In the biology also we know it as a biomethylation process. So, this particular methylation process is useful. Metallions are also getting methylated out of this. So, in all these typical organic molecules or organic backbones, if you go for the alkylation reactions, and one such simple example is you take isobutene, and two of the isobutene, if you try to attach it, that means the dimerization of isobutene, in that particular case this material can function as a good catalyst out of that. Then we can go for the production of large amount of inorganic fluorine products used in the etching, as I told you, etching of the glass surface, polishing of the glass surface also, that if we have unwanted silica material over the glass material, so that unwanted silica or SiO2 can be removed by reaction with your HF as SiF4, and that will go as SiF4 is a gaseous material. Then pickling of the steels basically, so is a particular process of steel making material. So one particular process of pickling is being done with this, and the manufacture of semiconductors. So for the semiconductors also the fluorine based reactions are also utilized. So these starting materials can function as a very good material for making for all these, and therefore useful for the semiconductor industry as well. Then we quickly see now that, as already we have seen, that how aluminum fluoride is forming. So this aluminum fluoride can be utilized for the formation of all these things. So raw material for electrolytic manufacture of aluminum. That means now you see that AlF3, your AlF3 is nothing but your typical material for aluminum production. If we are able to convert that as alumina from the bauxite to aluminum trifluoride, that means you require to supply the fluorine over there, and that particular one we can get it from your fluorspar itself. So now enrichment, the quantity or the amount of aluminum fluoride in a particular material should be enriched such that this can be converted to your cryolite, synthetically prepared cryolite, if you are able to make it in industry, not that naturally available cryolite, which is Na3AlF6. One particular process is the Lurgi process. The Lurgi process is from hydrated aluminum oxide, that means hydrated alumina or the bauxite you use, and we get it for this particular purpose, that since we are considering it as a hydrated aluminum oxide, we can consider it as, if it is hydrated and if you have large amount of water of hydration, what you write? You write the formula of this Al2O3 as Al2O3 dot 3H2O, center dot 3H2O. What is that? We are not able to say it as it is typically aluminum hydroxide, the way we get aluminum hydroxide precipitation from a reaction medium, even in a test tube. If you have aluminum solution from alum or aluminum chloride or aluminum sulfate and add some dilute alkali, you get immediate precipitation, white precipitate of aluminum hydroxide, gelatinous white precipitate of aluminum hydroxide. So that is typically aluminum hydroxide, but if you keep that aluminum hydroxide for a longer period, you can go for its corresponding removal of water molecules over it, and it can be converted to alumina. The formula of it is Al2O3. That means not that each and every aluminum centers will be attached to your hydroxide ion. Instead of that, you have a network of aluminum centers, aluminum as Al3 plus with oxide ions or the hydroxide ions. So when these oxide and hydroxide ion giving you a typical network structure, the formula what we would write is as the 3 water of hydration, which is equivalent to that of your alumina plus 3 water. So if you take that hydrated aluminum oxide from any other source, there is no need to think of your level of hydration, whether it is a monohydrate or a dihydrate or a trihydrate. What you consider is that you take it and heat it from 300 to 400 degrees centigrade, and up to that point, so all the moisture content will not be there, the moistures will be removed. Then whatever amount of hydrated alumina you have will be converted to pure Al2O3, that means water free Al2O3 with 3 water which is being removed from there. So, the dry Al2O3 what is there in your hand, definitely it will be dried at this particular temperature, can be utilized. So, if you make it and you transfer from one chamber to the other, what happens? That it is moving from one chamber to the other, but the reaction chamber is a different one now, which is kept at a higher temperature and with the introduction of your hydrofluoric acid. Even your HF gas is also useful. So, your Al2O3 will now be attacked by HF at 400 to 600 degrees centigrade, giving you now simply AlF3, aluminum trifluoride, and again 3 molecules of water will be removed from there for taking this as the corresponding oxide of the aluminum attached to it as water molecules. So, you get aluminum trifluoride. Then that aluminum trifluoride can be converted to your hexafluorosilicic acid also. So, the conversion what we get it as that AlF3, then you can convert it to your hexafluorosilicic acid corresponding one, that means instead of your this thing that you get it as aluminum as your aluminum fluoride, but now you use hexafluorosilicic acid as the material. So, this hexafluorosilicic acid material which is now supplying your fluoride ions, not your HF, not your sodium fluoride, not your ammonium fluoride. As we have seen that very easily we can also make hexafluorosilicic acid. So, this hexafluorosilicic acid is your now material to attack your dried aluminum, that means the hydrated aluminum also, that means just only AlOH3, not that Al2O3. So, since this can also be an acid form, so this is also this, so you get it as so along with the production of silicon dioxide at a very low temperature. So, is the Chemi Lynch AG process, so is the name of a German company, so that company they are producing it through this particular process. So, very easily basically without maintaining a very high temperature, only thing that expensive part of this reaction is your availability of your H2SiF6. So, that H2SiF6 what is available over there, you can the raw material, that means the hydrated alumina you can directly use for your conversion of this typical aluminum hydroxide to your aluminum fluoride. So, you get it. Then another one procedure is can be considered as a very big one or a very elaborate one, but do not be bothered about this all these things, but only you stepwise you look at it. So, in a single shot I am showing all these things because I have to go quickly little bit some time, because already I told you all these things. That means instead of all these things, that means your hexafluorosilicic acid, if you now use it for its reaction with only the ammonia, liquor ammonia or aqueous ammonia or ammonia gas. So, with ammonia it is simply giving you ammonium fluoride, that means ammonia will be converted, you have corresponding acidic ion from this part or hydrogen ion from water molecule giving you ammonium ion, and that ammonium ion will be able to take your fluorides from your hexafluorosilicic acid to making you ammonium fluoride. So, is basically some amount of a indirect process, and that indirect process is being utilized for the formation of now ammonium fluoride. Earlier what we are using the corresponding direct sodium fluoride or HF or corresponding hexafluorosilicic acid. Now you utilize the ammonium fluoride, but it is again we are getting from hexafluorosilicic acid, but all the different processes can have some advantages. And the different companies they are utilizing all these things because these are all industrial trade secrets, they are all patented or patent protected. So, they are basically going through different procedures depending upon the availability, the easy availability of the material and their cost. So, once this particular one, that means hexafluorosilicic acid is converted to ammonium fluoride, then ammonium fluoride is utilized to attack your alumina, that means your bauxite, to giving you something which is basically a salt of ammonium hexafluoroaluminate, which is basically very similar to that of your cryolite. which is nothing but Na3AlF6. So, instead of Na3AlCF6, it is ammonium AlF6 and some amount 0.05 mole of Al2O3, the bauxite. So, some amount of bauxite is still remaining, because sometimes the inherent character of that particular, the second reaction which is taking place at 100 degree centigrade, the inherent property of this particular reaction is such that whatever amount of ammonium fluoride you increase, you may not go beyond that. So, it is the nature of that particular reaction, it is controlled by its thermodynamic or catalytic character or the corresponding kinetic character, that it will stop there. Basically, you cannot remove the entire amount of Al2O3. So, some amount of Al2O3 will still be there, and we get that particular one as the raw material, and the challenge is that you have some amount of extra fluorine, because you are looking for making aluminum fluoride is only making AlF3, but the other part which is a similar compound, a similarity with that of your chloride, which has 6 fluoride ions around the aluminum center. So, you have excess fluoride. So, if you are able to take that excess fluoride from that particular first part of the unit, that means NH4 whole 3 AlF6 by this Al2 of the alumina Al2O3, then we will be able to make it as the entire amount of aluminum available as aluminum fluoride. So, the process is that, though it is a very simple 3-step process, but again for this particular material you increase the temperature to 500 degree centigrade. So, when you increase this temperature to 500 degree centigrade, the salt, that particular type of double salt type of thing, when you have excess alumina in it, is basically decomposed at that particular higher temperature. So, high temperature solid state reaction can now give you the corresponding very straight cut conversion of the entire amount of aluminum available in it to aluminum trifluoride. So, the whole amount of this, so 2 of this molecule heated at 500 degree centigrade is converted to aluminum trifluoride. So, AlF3, and this AlF3 can remove the entire amount of ammonia as NH3 and water molecules. So, we have now in your hand the AlF3. So, next day we will just move from here, that how we utilize this AlF3 to some useful purpose, whether we go for its conversion to some cryolite formation or any other thing, such that this fluorine bearing compound can be useful for your industrial purpose. Thank you very much.